and welcome to SciLux, the podcast where we talk about scientific developments and technological changes in Luxembourg. And in today's episode, we are talking to Andrew Ferrone. Andrew Ferrone is a physical climatologist by training and works primarily at the interface between climate science and policy. He is currently the head of the Meteorological Service of the Administration of Technical Agricultural Services, ASTA, in Luxembourg. He is also the permanent representative to the World Meteorological Organization, the head of the Luxembourg delegation to the Intergovernmental Panel on Climate Change, so IPCC, and the president of OPC, so the Observatory of Climate Policy in Luxembourg. Andrew, thank you so much for coming today.
Thank you very much for the invitation.
I'm already happy because I managed to do the introduction without many takes, and there were a lot of different organizations. So, it's never easy with the long names of organizations. You didn't make it easy on me, but I don't think you can choose that, right? At least OPC is short.
Yes.
That's a good thing. Okay, good. I mentioned that you're a physical climatologist. I didn't say that you have actually a PhD in that. That's why also you are here, because of course we talk to researchers. So I was just wondering, because I think that, I don't want to mention your age, but when you got the PhD, it was a couple of years ago. So most probably climatology then was very different than it is now. Am I right in assuming that? Has it changed a lot, the sphere? Is it now focusing mainly on climate change or not?
Yeah, so the field of climatology has indeed changed a lot since I did my PhD. One of the big differences is the broadness of the field. When I was studying, it was actually mainly on physical climatology. There were some geographers involved, but today we also have biologists involved, for example, also social sciences involved, economists involved. So it has become much broader. We also see it in the IPCC report, where I had the privilege to be part of the approval of a part of it in 2007 of the fourth assessment report. And it was much narrower than it is today. Also, the number of literature has exploded. It has increased more than 10 times from one report to the next. So we are now even talking about using artificial intelligence to assess the literature that is out there, because humans can just not do it anymore. And another point that I think there was a big evolution was on the attribution of climate change. So when I did my PhD, during my defense, if I would have said that the heat wave of 2003, which was a big topic at that time, would have been even partly due to climate change, I would have failed immediately my defense. Whereas today, so there was a new field of climatological science that evolved in the last 5 to 10 years, where you can actually say, okay, this meteorological event has actually been due partly, at least, due to climate change, or even completely. If we wouldn't have the human-induced climate change, this event would not have happened at this scale or this magnitude.
So that's a big change for sure. And of course, we can also say that in general, the extreme weather events that we are noticing are just very noticeable in comparison, right? I'm not counting, but the recent one that I was very surprised one was the flooding in Dubai.
Yeah.
It was really, really surprising because, that's maybe not that close because it's not Luxembourg, but it's very tangible and you can see that there is something going on.
Absolutely. So this attribution comes from two parts. First, science has evolved, but also climate change has evolved. And so now we are out of the signal to noise ratio, as we call it internally. So really the natural variability, the events are just outside of this natural variability that was there in pre-industrial times, or even like 60 years ago. We are completely out of that range. So that's why these attributions can happen. And the Dubai floods was one example where it was also already published that climate change played a role, but also the flooding here in Luxembourg in 2021. There was also an attribution study done there, and I was actually also part of that one. And there we also came to the conclusion that the magnitude of the rainfall as it happened, which led to the flooding, was influenced by climate change, and also the frequency of such events is indeed influenced by climate change.
So we have all these confirmations, but at the same time, I still have a feeling that there's so many people that just say, nah, climate change now. I am in a bubble. So I feel that all my friends and people around me are kind of convinced. But still, there are so many people who are not. How come? What's going on? Why they still the science is just not reaching such a big percentage of our society?
Well, it's difficult to say. I think there are different categories. There are still, and I think this part of the population is, however, decreasing. People saying that climate change is not happening at all, because with what we see outside, I think most people are convinced today that climate change is happening. Then you have a part of the people who say, well, this is natural. I think there it's really a problem, because they hear that climate was changing in the past, which is correct. We have glacial, interglacials, and so on. But the rate of change was completely different. I mean, what we have seen now, this 1 degree, 1.1 degree on the global level that we have witnessed in the last 150 years, basically, for between a glacial and interglacial period, it would have happened over 1,000 years, probably. So it's a completely different scale of magnitude. And maybe that's a point that has not been yet made clear enough, that it's the range of change that makes people really understand. And the other point is that some people don't have the feeling of what the word theory means. I mean, if you look at other fields of science like astronomy, they are also all based on theory. And still we know that this is the best representation of truth that we have today. And for the greenhouse effect, it's the same. Yes, it is a scientific theory, but we know that this is the best explanation we have today. Of course, there are always new ways to discover, but the IPCC in its last report was clear. They say it's unequivocal that climate change is happening, and it's also unequivocal that it's due to human emissions of greenhouse gases. So there is no questions out there today that it's due to humans.
Yeah, and this is very important to say that and to reiterate that we know it and we are sure, right? Because, of course, this is one of the problems. I also think that the discussion about climate is at the forefront of problems with science communication in general, right? Because you're really fighting the battle of trying to convince as many people as possible to take the science out there, explain it, and actually succeed in it, because it's a very dire and important need that the people understand it. And it shows how difficult it is, because, of course, as you said, we have theories, and scientists cannot sometimes say we are 100% sure. But in this case, we are sure.
Yeah. Absolutely.
Exactly.
Yeah.
And that's what IPCC is saying. And you can read the report, you can check that out. Yeah. And for sure, in the notes, we will be sharing all the links. There are also very interesting summaries out there that you can find for IPCC if you don't feel like reading the report, because all the reports, that's how many already that we can read?
So we have now finished the 6th assessment reports. I would recommend looking at the last one. Actually, there is a synthesis, because the IPCC works with 3 working groups. So all 3 working groups have published a report in the last cycle. And we had an unprecedented number of special reports. So we had 3 special reports, so a total of 6 reports. And all of them are actually synthesized in the synthesis report. So I would, for those who are busy, I would really recommend looking at that one. And I think there is a lot of information in there.
Okay, so we are going to explain what IPCC actually is in a second. But first, I wanted to ask a question. Before we started recording, I was telling you that this is a question that I had to actually study with my son recently. But I also had a feeling, if I were to explain it myself, I would have a problem. So we talk a lot about climate and we talk a lot about weather, but what's the link? What's the difference between weather and climate?
The main difference is, if you want to put it into one phrase, climate is what you expect, the weather is what you get. So climate is basically a statistic over a long period of time, like normally 30 years. That's what's used by the World Meteorological Organization, the WMO. Some also, like the IPCC, are using shorter time periods, but 30 is the usual one. And then you do statistics of your meteorological observations over these time periods. The most obvious statistic is the average. We always talk about average temperatures, average rainfall, but you can also go to percentiles. You can also do quantiles and so on. So there are different statistics that you can do, which describe what you observe in one point at during a certain period of time. The weather, however, is then all that is superimposed. So as we know, for example, the weather we can only forecast for the next 5 days 10 days if the situation is very stable, like if we have a big heat wave, typically, then we can say, okay, it will stay for like 10 days. But typically, weather is limited to 5 days. And this is due because from a scientific point of view, it's a chaotic system. So it's very sensitive to the conditions that we measure. And each measurement always has uncertainties. And because of the chaos in the system, the uncertainty propagates very strongly. Often we talk about the butterfly effect. So if a butterfly flaps with its wing, it can create a hurricane in another part of the world. Even if you would have the perfect weather model to predict, which we don't have, because also there are uncertainties. But even if we would have it, these uncertainties would propagate and limit the time we can do weather forecast. That's something that meteorologists have to work with. There are in certain parts of the world now forecasts that go a bit longer. You can also find them on the internet also for our region. And these are then based already on statistics. So they tell you, well, this summer there is a certain probability that it's warmer than average, or there is a certain probability that it's wetter or more precipitation than average. So that is existing. My personal opinion is that in our region of the world, it is not working a lot. Often it has a chance of 50%, which is basically a coin. And then the next step will then be to go to climate change, because there you can prove mathematically actually that again, you come to a deterministic system. And so that means that you can actually predict it. So if we would know exactly how the emissions would evolve in the future, then we can actually say that's what the climate is going to do. However, we don't know, because we know that it is based on human decisions, how emissions of greenhouse gases are going to evolve in the future. So that's why we are working with scenarios. So we say, okay, in the best case scenarios, this is going to happen. So emissions are going to decrease very rapidly to net zero CO2 in 2050. And then we can say, okay, our models show in that case, we reach 1.5 degree. The longer we wait for net zero CO2, the more the temperatures will rise to 2 degrees, 3 degrees, and so on. And in that case, we talk about projections, because it's based on hypotheses. It's based on a hypothesis, how will the future evolve? Because we have no crystal ball to know what humans are going to do in the future.
What I noticed also in the literature was something that was called climate model. And what is that?
There are different kinds of models, but the big climate models is basically where you try to represent the whole climate system in a computer code. So you, of course, have the atmosphere. So you're calculating the winds, the temperatures, the precipitation. You have the ocean, which is also a very important part of the climate system, because it absorbs 90% of the excessive energy that we get due to the reinforced greenhouse effect. Then you have all what is related to the cryosphere, so everything which is related to glaciers, the ice sheets, and so on. You also have them in these models. You have the biosphere, everything which is biogenic in these models. In practice, often they are based on weather models. So actually they are working a bit like a weather model, a bit more complex than a weather model, but then you run them over hundreds of years. And in that way, you can actually then do projections for the future. So first you check, are they correctly representing the past? Because that's where we know what's happening. So we see, are they correctly representing the past? For the moment, we can say yes. And then you run them. So again, as I said previously, you assume a certain emission pathways, and then you run them for the future, and you see what is the outcome. How is the temperature going to change? How is the precipitation going to change? How are the weather patterns going to change, and so on. And again, you don't evaluate them for single years, because we cannot say how the weather will be in 2100, but we evaluate them over longer periods of time to have really the climate signal.
That sounds very much to me like machine learning models then. You're also giving data and you're perfecting your model in order to get a prediction, or not really?
That's the next step. So This is something that is happening actually right now. They are based on machine learning. Up to now, they were not yet based on machine learning. So, first you have the basic equations of the atmosphere, which you can solve in your computer code. So those don't actually need what is called tuning. But then you have also some phenomena that you cannot exactly prescribe. For example, very local precipitations, which are, however, important, like thunderstorms, for example. They are important for the global system. So if you don't have them in your models, your model will go wrong. So you need somehow to give the model the information what these thunderstorms or storms or in general are doing on the grids that are in your models. And actually these need what is called tuning because they interact with each other. And so you actually calculate the past and then you see, okay, my model is not doing this part correctly of the climate system. So I need to give it additional information to do it. Up to now, this was done by expert judgment. That was indeed part, for example, of my thesis and also of my postdoc. I was doing that. But now you are right that indeed we are going towards artificial intelligence and we are using artificial intelligence to even get more information out of these models.
You mentioned before emissions, so we have to go back to that. Obviously, we're talking greenhouse gases and we're talking emissions. Why are they important and what is happening in that sphere?
The greenhouse gas effect is based on the greenhouse gases. So there are particular gases in the atmosphere. The most important one is actually water vapor. We often don't talk about it, but the natural greenhouse gas effect is to a big extent due to water vapor, which is in the atmosphere. The concentrations of water vapor compared to the other greenhouse gases is quite high. So the direct influence on humans on water vapor is actually not that big. That's why we don't talk so much about it. The one we really talk about is, of course, carbon dioxide. Then we also have methane. We also have nitrous oxides. So all these are greenhouse gases. And what they are doing is that, so there is an energy equilibrium between the sunlight that we get in from the sun and the radiation that goes out from the Earth, which is in the infrared spectrum. And actually, the greenhouse gases, they mainly absorb the infrared radiation. That means they sort of create a cover around the globe. Without greenhouse gases at all, like for example, if we look at the moon where we don't have an atmosphere, the average temperatures are around minus 15 degrees colder than what we have today if everything else is kept constant, because there would be other changes. So it would be a little bit different probably, but assuming just back of the envelope calculations, it would be 15 degrees colder than what we have today. So actually the natural greenhouse effect is good because actually it allows life to evolve. However, what we are doing for the moment is that we are pumping more and more greenhouse gases, especially CO2, into the atmosphere. And so we are increasing this natural greenhouse gas effect. And that's where things become problematic.
And moreover, CO2 is cumulative, right? So for example, for methane, we discuss it is important, but the moment we stop releasing methane, the equilibrium goes back. Whereas with CO2, even if we stop, it's still going to be there.
That's correct. Yes, that's indeed a big difference between CO2 and other greenhouse gases is that it's cumulative in the atmosphere. So once it is out there, it actually stays for thousands of years. It is, of course, in the cycle. So there is a so-called carbon cycle because we know that there are other natural emissions of CO2, like, for example, out of certain biological processes, but also the oceans. They sometimes release CO2, but at the same time, they also absorb CO2. Also, trees are absorbing CO2. And so before human intervention, all this was in an equilibrium. But now, due to the human emissions of greenhouse gases, they are accumulating in the atmosphere. Actually, 1/3 of our emission is for the moment absorbed by the biosphere. So we are lucky. We actually have a service that the biosphere is providing to us. So 1/3 is absorbed, but the rest is staying there, and it's staying there for thousands of years. So that's indeed a big problem. And that means actually, and that this is very clear in the last IPCC report, that we need to reach net zero CO2 emissions in order to stabilize climate. So it's not like with other environmental problems that once you have gone away with the problem, usually the systems try to recuperate. But for climate, in order to stabilize the system, we actually need to reach net zero CO2 emissions. And we need also to reduce the other greenhouse gases like methane and nitrous oxide by approximately half of the emissions that we have today.
So it's not enough that we just find solutions. I don't know, we talk carbon capture or we just plant a lot of trees.
No, that's not enough. That would be nice. So actually, the estimation for the moment, the IPCC was not that clear what is possible. But for just the plant-based part, we can probably cover a big maximum of 10% of our emissions. To do this, first, we need, of course, to stop deforestation, because for the moment, the land sink, as we call it, is actually an emission. So it's not a sink, it's actually emitting, because we are, amongst others, deforesting. Also, other agricultural practices are also emitting from the land surface, but deforestation is for the moment still the biggest. So first, we need to stop deforestation, and then we actually need to plant more trees again in order to increase the sink. But even in the most optimistic scenarios, we could maybe cover 5 or very optimistic 10% of our current emissions. So 90% have to go. Of course, there are also technological ways to get CO2 out of the atmosphere. There is also an active science research going on this field. Here, of course, the problem is, first, for the moment, they are pilot projects. So we don't know, can we scale them up? Also, they need energy. So the energy needs to come from renewable sources, which we cannot use for other uses in that case. And the final problem is we need to store this CO2 somewhere. And this needs to be a very secure storage, because if it starts to leak again into the atmosphere, then we recreate the problem for the future. So there are clearly risks involved in the technology. Probably it will be part of the solution too. But also here, I think for the moment, the number of 10% of current emissions being, so to say, compensated by CO2 sinks seems to be a big maximum. So we do need to reduce the emissions, real reductions, by 90%.
And talking of reduction, I know that your pub quiz question is related to that a little bit, because, we don't want this episode to be only talking of all the different problems and issues we have. We want to talk solutions too. So if you can ask the question, and listeners, remember, answer to the question only at the end of the podcast.
The question is, with a carbon price of $100 per ton of CO2, how much can we actually reduce the emissions up to the year 2030?
Okay, and remember, answer only at the end, unless we touch upon it, but I'll try not to lead you to that. I don't think we mentioned that, so there's a F word we need to mention, but not the bad one. It's still pretty bad in climate discussion, which is fossil fuels, right? Because we said emissions, but the emissions, these are fossil fuels. That's what we need to work on, right?
Correct. Fossil fuel emissions are responsible for the biggest part of the CO2 emissions that we have. And that's really the transition that we have to go to in order to achieve this climate neutrality, to move away from fossil fuels and go to renewable energies. They are, in fact, the cheapest one. I don't say the price now, not to go to our question. They are indeed cheaper, and it has been shown now that actually renewable energies are cheaper than fossil fuels for now. So they have reduced dramatically in price, much more than expected from the 5th assessment report of the IPCC to the publication of the 6th assessment. It was nearly 10 times going down in price, and they are now cheaper than fossil fuels. So also economically, it doesn't make sense anymore to invest into fossil fuels. Also, for the grid infrastructure, it has been shown by studies that, for example, in Europe, we can have a stable grid with renewables. So there are scenarios in the IPCC report. So there are approximately 5,000 scenarios which have been assessed by the IPCC for the latest report. And there are scenarios in there where we completely switch to an energy production by fossil fuels, even taking into account the increased amount of electricity that we need, because there it's clear that we need to electrify some of the systems, like transport needs electrification. Also, other sectors which are heavily relying on fossil fuels need electrification. So there is an increase in need of electrification, but it can be covered by renewable energies.
We keep mentioning all those names like IPCC, so I think this is the moment to de-enigmatize, can you say that in English, all these names, because I have to say that I'm following the space, but I'm still a little bit confused, because we have COP, we have IPCC, we have WMO, as you mentioned, and also you actually are responsible, let's say, for the latest report of... what's the name? I never remember. European State of the Climate. Yes, sorry. So, all this, is it all together? Is it separate bodies? What's the relationship? What's the link of all that?
They are all separate bodies, actually, but of course interlinked. So let me maybe start with the oldest one. That's the World Meteorological Organization, which was founded in 1950. It had a predecessor before the Second World War, but it was not yet global. It was really, so the UN system was found after the Second World War, and the first agency, the UN agency, was actually the World Meteorological Organization. At that time, the main idea was really to share meteorological data, because we discussed about it before. It is actually for weather forecasts, it's very important to know ideally all the information that you can get all around the globe. Just to give an example, it has been shown that if we would have more weather observation in the South Pacific, our forecast, our 10-day forecast in Europe would actually increase. So there are interconnections all around the globe. So having all information you can get on the weather is very important for weather forecasts. And that's actually why the WMO, the World Meteorological Organization, was founded in 1950. So at the beginning, it was really to collect data from all national meteorological and hydrological services of the world, to share them between them so that they can all do the forecast using their neighbors, because neither weather nor climate stops at the border. So that was the first idea. And then also to standardize these measurements, because if you, for example, measure temperature at a height of, let's say, 0.5 meter, 1 meter, 2 meters, 10 meters, and at the same spot, you get very different measurements, because the temperature is increasing with height in normal weather conditions. So that's why, for example, we have the standard today to measure temperature at a height of 2 meters. So all around the world, it is measured at a height of 2 meters. And this is a recommendation by the World Meteorological Organization. So the WMO is a very technical organization. It also produces reports. So it also works together with scientists. But these reports, for example, they are not approved by the members of the World Meteorological Organization. So we have 195 members of the World Meteorological Organization. That's all countries of the world, plus some specific regions. But these are not actually approving the reports of the WMO. I'm insisting on this because that's one of the major differences with the IPCC, the Intergovernmental Panel on Climate Change, which was founded in 1992. The IPCC is independent, but it has two parent organizations, the WMO, which we mentioned, and the United Nations Environment Programme. So they are both giving, for example, the secretariat to the IPCC. The IPCC has the mandate to produce reports, actually to assess all the scientific community. So it doesn't do research on its own, but it assesses all the research that is out there, both on the physical science basis, but also on adaptation, on vulnerability of climate change, and then also on what we call mitigation, so reduction of greenhouse gases. So it also goes very deep today into the solutions page, because the scientific community often it's seen as political, but actually the scientific community can help politics to really find the right solutions to the problem. And what is always important to keep in mind for the IPCC, which also here sometimes outside, it doesn't give recommendations because it's policy relevant, but not policy prescriptive. So it will never say, this is what you need to do. It will say, okay, if you want to limit climate change to 1.5 degrees, well, you need to bring down CO2 emissions to net zero CO2 by 2050. But it will never say you have to do this. That's a big difference to understand. The IPCC, it has the same members than the WMO, so it also has 195 members. And actually, the reports are then also approved in a dialogue between the members of the IPCC and the scientists. And I very much insist on this word dialogue, because what is important to know is that the scientists are those that have the last word. So it will never be that the government can impose its views or so on the scientists. It's all done by consensus, but it is always the scientists who have to say, okay, if this sentence is fine for everybody, we can write it down as this, but it has to be scientifically correct. That's really important to emphasize. So they are scientific report, but they already get a sort of first touch by the policy side. So it's very much this policy science interface. Then the last part is what you mentioned, the COP, the Conference of the Party. Actually, they are happening under both the United Nations Framework Convention on Climate Change, the UNFCCC, and the Paris Agreement. They both have actually their own COP, and these are political decision-making bodies. So all countries that are a member of it, and there are 197, there we talk even about parties, because, for example, the European Union is also a party of it, but it's not a country. So that's why we talk about parties, and all of them actually take together decisions or give a mandate to take decisions together. And again, it's all by consensus, which makes the process extremely difficult, but also extremely powerful, because nobody can say, no, I'm not going to do this because I did not agree to it. So they all agree to what has been decided at the COP. So these are done really political decisions. Like the Paris Agreement clearly says all the countries that are in the Paris Agreement, that is the same then as the UNFCCC today, they all agreed to limit climate change to well below 2 degrees, aiming towards 1.5 degrees. So everybody agreed to that goal, for example. Then they also agreed on different goals. And so each year we are meeting again to push it even further. We have now in Dubai the outcome that we want to double energy efficiency. We want to triple renewables until 2030. So we are getting in a very concrete space now where really everybody commits to fight climate change. It's also the first time, and this was in the fossil fuel producing countries, that actually we have written down that we need to move away from fossil fuels. So it didn't say we need to get a fossil fuel phase out. That was a bit much to ask, but still we had this message that we need to move away from them, which is a very powerful message, I think.
It's good to hear you talk about it, because I think as a layperson, when I hear about the conclusions of COPs, I'm not that hopeful, I have to say. It's very political, as you said, and it's difficult to see, especially seeing the urgency of things, to see that these are concrete decisions that are leading to something. They're very watered down, if I could call them like that.
I agree, they are watered down, but still they are extremely important because, well, what is important to understand is that it's not at the COP where none of the ministers who will be there will take on-the-spot decisions. Okay, we are going to do that. Of course, they all come prepared. They all have a little bit surprises in their hands and so on. But the real action will happen on the ground. I mean, if we think about Luxembourg, the action about climate change is our national climate and energy plan, which was adopted last year by the government. That's where the action comes to the ground. This is not at the COP where this is decided. But the COPs are very important because they give reassurance to everybody that everybody at least commits to move into the same direction. So nobody is going to hold back saying, okay, I have a problem if my neighbor is not doing the same, that I was not as ambitious as I am doing. So it gives the countries a possibility to discuss between them and see where are we on the level of ambition. Of course, it is clearly not enough. Emissions are still increasing, so we are not on the path to meet 1.5. This is very clear. But the IPCC has also shown that before the Paris Agreement, we were on a path to above 4 degrees in 2100. Whereas now we are on a path to nearly 3 degrees, which is well above what the Paris Agreement has promised, which is something probably that we cannot adopt to. So it is not a good world we are for the moment heading to. But in these 6 years that have happened, we have seen that we came already down, so to say, from a pathway of 4 to 3 degrees. And there are now more and more things happening, like renewables are growing really, really fast in the world, that actually give hope that this will continue to increase. And so that's why these COPs are so important in order to really get this, because it's a global problem. We need the global confidence that countries can be as ambitious as possible.
But then if you say that in 6 years we managed to decrease it by 1 degree, we need 1 more degree, basically. So another 6 years should work. Or it's more, it was easier for that 1 degree and now it's the struggle.
Maybe the first degree was indeed a bit easier. I agree, but I think there is still a lot of room for improvement, and things are moving now. Some economics even think that some decisions that have been taken, but also some economic transition that have happened towards renewables, for example, they are actually, even if the politics decides to go into the other direction, they cannot undo them anymore. So this, the stone is rolling now, so to say, and it's very difficult to roll them. Some are even talking about economic tipping points, that we have, either we are very close or we have already triggered some of the economic tipping points. So for once we have positive tipping points, I have to say. There are also a lot of very scary tipping points out of there, but these economic ones, some have now evolved and they are moving. But we have also to say, for the moment, a lot was based actually on technology. So we have changed the technology. But now the next step will also be to change lifestyles. That will, of course, be much harder to do. So yes, it is getting harder, but still there is a lot of potential out there.
I'm happy we are so hopeful. We said IPCC reports and the other different discussions, but we didn't mention the European State of the Climate. So how does it fit in to all the picture?
Correct. I forgot that one. So this one is actually for the first time this year produced by WMO and by the Copernicus Climate Services. So the Copernicus Climate Services is put into place by the European Commission. It is housed at the European Climate Center for Medium Range Forecasts, ECMWF. So that's a sort of European weather service. And they got the mandate to get together all data related to climate change, partly, for example, coming from the IPCC, but also from other sources, again, also from meteorological stations throughout Europe, but also global, and then also from satellite observation and so on. So they are putting all this data together, and on their website, it is possible to find them. And then actually, for the first time, this time we had the WMO and Copernicus producing this European State of the Climate report. So it is based on actually a report that the WMO started like now 15 years ago, which was the Global State of the Climate report, which are now published each year just before the COPs in order to inform the COPs about the latest state of the climate. Again, it is to really increase ambition at the COP to say, okay, we are definitely not on the right track. And then it was decided 3 years ago to also have regional reports. So in the WMO world, the world is divided into 6 regions. Region 6 is the European one. And now for 2 years, we had actually a report coming out by the region 6 of the WMO. But in parallel, Copernicus was also doing a state of the European climate report. So they were very close. They were not identical, but very close to each other. And so for this year, for the first time, we decided to actually work together, have one common product, which we published on the 22nd of April.
And do you see any specificities for Europe when it comes to climate change and what you compiled in the report?
Yeah, one of the specificities is that Europe is the warmest, the region of the 6th region of the WMO that is warming the fastest. This has several reasons. One of them being that, for example, the Arctic is a major part of the domain that we are looking at. And we know that the polar regions are warming faster than the rest of the world. Of course, there is a lot of land surface in it. We also know that the land surfaces are warming faster than the ocean. emissions. So that's not surprising. But then also another factor that is contributing to it is that in Europe we have been very successful in reducing air pollution. But these emissions actually also were hiding part of the increases in temperature in Europe, because they were reflecting the solar light, and so they were hiding the increases in temperature. And that's something we are seeing now in Europe. We expect it for other parts of the world too, because they are also working on air pollution reduction. But in Europe, we already saw it. So these were the three main factors that explain why Europe is the fastest warming continent in the world.
And this is also an interesting part that I was actually not aware, only learned about it when I was preparing for our discussion, is that exactly the pollution actually helps reduce the temperature a little bit. So in a way, we're trying to get rid of the pollution, but then we have to think about that effect you mentioned, that this means the temperatures will rise.
Yeah, that's correct indeed. But this is also actually included in the scenarios of the IPCC, because often air pollution reductions and the move away from the fossil fuels actually work together, because a big part of the air pollution comes from burning of fossil fuels. So if we burn less fossil fuels, we automatically address also air pollution. So this goes together. Indeed, it is a problem, but at the same time, it also helps certain aspects of climate change, because, for example, especially the soot particles, they deposit on glaciers, they deposit on the ice sheets. So actually, in that case, they make them a bit darker, so they can absorb more solar light, and so they melt faster. So if we indeed reduce these emissions, we also help that glaciers and polar ice sheets will not melt as fast as they would be with this pollution. So it has a little positive effect also there, also related to climate change. But indeed, the main effect is that climate change will be accelerating.
This is fascinating. You really need some kind of systems thinking, because it's all interrelated, as you're showing. And what was interesting also in the report is that it looked at the health aspect of climate change in it.
Yeah, correct. That was a focus of this year. So we always have a climate policy part of the report each year. This year we looked at the health aspects. Again, the news are not good. We see that there are an excessive amount of people dying in Europe due to heat waves mainly. It is always one that is a bit difficult to assess, because you can also only assess it with a certain delay. So we couldn't give exact numbers yet for 2023, but this is going to come. Nevertheless, we see that the number of people dying due to heat waves in Europe is increasing at an alarming rate. However, we also see that there are good solutions out there. For example, greening of cities is an interesting solution. Also, you can even think it much closer, putting the green infrastructure next to the houses, because then you avoid installing air conditioning, because air conditioning is using additional energy, which will be more difficult to get in the future. So in order to avoid this, you rather could green houses. For example, you start with the roofs, but you can also put it around the houses. But then also squares have to be greened. Of course, the warning of the population is a very important one. Warning is one thing, but information is also important, because it was shown in the report that in Europe we have one of the best warning systems, but often people are not aware what is the right thing to do in case there is, for example, a heat wave, or if there are floodings, what are the gestures to do. So you also need to inform people, if there is a warning coming, how to react to it.
Well, I think this is the moment to go back to, all the solutions. We already started a little bit. So let's start actually with solving the pub quiz question, so we can talk about one solution and then we'll talk about the others. So if you can remind our listeners what the question was, and then please give us the answer.
So the question was, how much can we reduce emissions with a carbon price of $100 per ton of CO2 until 2030? And the IPCC assessed that it's around 50%. So it is a big part of the solution, which is actually at a quite accessible price. To be more precise, even like up to 20 or 25% of reduction is even at negative price. That means, of course, you have to invest, for example, for renewables. You have to invest, build photovoltaics, build windmills. However, at the end, you actually save money because they are cheaper than fossil fuels. So they even come at negative costs.
Okay, but that's always the problem of the, reward that comes next, right? There have been a lot of psychological studies with children, right? That they know that they will get more marshmallows if they don't eat that one they got. But, we have a problem with that. But it's very good to know. It's very important. So remember, that's the first thing. What else? How do we fix it all? Let's be positive a little bit. You said we have solutions in the European State of Climate report. We have solutions in the IPCC report. So if you can share some of them with us.
Yeah, there are many solutions out, and I think what is important is actually that many of the solutions bring a lot of benefits. I mean, in Luxembourg, a big part of our emissions is, of course, due to transport, for example. And just to say here, well, the first thing you think about when you think about transport is to electrify the transport. And this is clearly part of the solutions. However, we also have problems with traffic jams in Luxembourg. And even if we switch all our cars to electric cars, we will not solve the traffic jam. So if we have a better public transport system, and also if people think to go more by foot or use rather the bike than using the car each time, we have less cars on the road. And so actually we can have a better life quality by going to the public transport. So you can actually have multiple solutions in the same thing. So part of it is technology, switching to electricity, but part is also behavioral change, switching to public transport, switching to more walking, which is good for health, by the way, switching to biking, which is also good for health. So all of this works together. Another example where often people are also a bit confused is how we are eating. So the food system actually represents 1/3 of the emissions worldwide, which is a big part of it. But what people often think is that a big part of it is transport, which is not the case. So of this 1/3, only around 10% is due to transport. So actually the transportation of the food, even around the globe, is not this big issue. Often you hear a campaign that you should eat more locally. This is not bad because we need to support the local agriculture and local farmers, which has a good idea by such, but actually it doesn't reduce really your carbon footprint of your diet. What really matters is everything which is related to red meat and also to milk products. So that's the big chunk of it. I can also show it by data here in Luxembourg. So if we reduce to this, again, we don't need to completely get out of it, but if we reduce it already a lot, we can already reduce our footprint a lot. So going more vegetarian, even vegan, is part of the solution. But the other part is also food waste, because it has also been shown that worldwide, 1/3 of the food that we produced is wasted. So again, if we would reduce this to nearly zero, if we make the calculation, so we have 1/3 of the global emissions, 1/3 is food waste, so that's 1/6 of the emissions that can be reduced by avoiding as much as possible food waste. So that's really something that you should keep in mind when you do your shopping. Do I really need what I do my grocery shopping for? That's another important point. So these two together, switching the diet, which again helps the health, because it has also been shown that the diets we have from the moment here in Europe are not healthy diets. So you do something good for your health, you do something good for the planet, for biodiversity at the same time, and then reduce food waste, then you can already reduce your impact of your food system a lot.
But then with the red meat and milk products, is it because of the methane that is produced, or is it something else?
Yes, it's mainly the methane which is produced during the dairy production.
So I'll remember that. I'm actually not eating that much meat, so I definitely suggest and walking. You can also follow Andrew on social media. I follow him on LinkedIn, and I noticed you recently had a super long hike. So, it's always good to look at people and what they're doing. And you're definitely a good example of what, after all these reports that you produce, I guess it stays in your head to be a good example for that. And what reminds us just to thank you very much for sharing all this very important scientific knowledge and what is going on, and unwrapping all the abbreviations for us as well. Thank you, Andrew, for coming today.
Thank you very much for the invitation.
And this is it for today. Don't forget to subscribe, to follow us, to write to us, suggest guests, and to communicate with us as much as you can. We are present in all the social media. And this was SciLux, and my name is Hanna Siemaszko.